Welcome to podcast 12.2b. What we're going to do is we're going to continue on those measurable properties. If you remember last time we talked about Boyle and we talked about Charles, and today we're going to talk about Joseph Gay-Lussac. And what Joseph Gay-Lussac found that if you kept the volume constant, and again it's all about having a certain number of variables constant, if you kept the volume constant, the pressure and the temperature were directly proportional. So that means if the pressure goes up, the temperature will go up, or vice versa. So you could think of it this way. Imagine an aerosol can, right? Oops. Any spray paint can, hairspray. You're sitting around the campfire, and you toss it in there. Now what do? Well, of course you run like crazy. And this is why we don't do this for fun, because imagine a can with a constant volume, right? Because that volume is, whatever the size of the can is. And we heat it up. Fire, we heat it up. What's going to happen? Well, eventually the pressure is going to get so great that it will overcome the holding capacity of the can, and the can will blow up. So you may not have known this, but Gay-Lussac's law is the reason we don't throw aerosol cans in the campfire for funsies. So like always, because we're doing measurable quantities, we can do some math here. So let's look at this. Same relationship noticed as the V over T. So let's just practice one real fast. By this time you're getting pretty good at these. It's probably a no-brainer. But let me just work this out. So I've got 2.87 ATMs at 47 Celsius plus 273, right? That gives me 320 Kelvin. And that equals P2, right? And let's see what this is. Standard temperature. Okay, standard temperature. Standard temperature is 0 degrees Celsius, which is 273 K. So I work that out, cross multiply, divide, and I get P2 equals 2.45 ATM. That's what my calculator says. Let's think about this now. What happened to the temperature? It went from 47 down to 0, or a better way to look at it is 320 down to 273. So the temperature went down. So we would expect the pressure to go down. And let's see, 2.45 versus 2.87. Good. It did exactly what we thought it would do. Again, one of the things I love about these problems is you can really do an easy self-check just by thinking about what should happen with the numbers. All right? Moving on. Mr. Avogadro, you guys know about Avogadro and the mole, but the way he developed his theory was really through gas laws. And what he found that it didn't matter what type of gas, if you had gases under the same conditions, they would have an equal number of particles, or as we know, an equal number of moles, right? Okay, and so basically the volume and the moles are directly related. And think about this. I've got a balloon, right? I'm pumping in more gas, right? More moles of gas. So if I'm putting in more moles of gas, what's going to happen? The balloon's going to get bigger. The volume is going to go up. And hopefully that makes sense to you. You pump in more gas, the volume goes up, okay? And here's another really good conversion factor that we're going to use quite a bit in a little while later. Look at this. If I have 1 mole of gas at standard temperature and pressure, and again, remember, standard temperature is 0 degrees Celsius, standard pressure is 1 ATM, right? If I have any gas, and this is hard for people to understand, but any gas, under those conditions, it will occupy this volume. 22.4 liters. And I have a box in my room that is that big, and I'll show that to you. It's actually, you've already seen it. It's that clear box that I have sitting in my room. I've done a couple demos in it. So that's about 22.4 liters. Okay? So anyways, that's a real good conversion factor that we'll come back to a little later. Now let's look at the last thing. Let's say I want to take Charles' law, Boyle's law, and Charles' law, Boyle's law, Gay-Lussac's law, and I want to put them all together. And what do I get? Well, I get this combined gas formula, which is P times V over T equals P times V over T. Now, the thing I like about this is, think about this. All three of them are there. What if I get rid of the T's? What do I have? Well, there's Boyle's law. P over V equals P over V, right? Well, what if I were to get rid of the P? Look at that. I have V over T equals V over T. Who's that? That's Charles' law. And then last but not least, what if I were to get rid of the V? Okay, I've got P over T equals P over T, and that's what we just did. That was Gay-Lussac's law. So in the combined gas law, they're all there together. And so you can imagine, as challenging as it's going to be, we're going to give you 5 conditions, and we're going to have to solve for a 6th one. Typically, a P2, V2, or T2. All right? So, of course, we want to try one, right? So let's try one. So there we have some conditions. And if you want, pause the video, try it, and see if you get the same answer I get. All right, did you do that? Well, if you got 1.55 liters, that's what I got. And if you didn't, then watch this. I've got a gas, 2.5 liters at standard temperature and pressure. So a standard pressure is 1 atm, right? And I've got 2.50 liters. All over standard temperature, which happens to be 273 K. And that all equals, let's see, I'm solving for, oh, there's P2, 1.73 atmospheres. Add, oh, I don't know V2, so I'm solving for V2. All over 20 Celsius, which, if you add that to 273, is 293 Kelvin. All right? So again, we've got the same kind of problem we've done. We're just going to cross multiply, right? We're going to cross multiply and divide. So when I multiply those 3 numbers together right there, I get 732.5. And if we wanted to write the unit, it would be like K times L times ATM. And that equals 273 times 1.73 equals 472.3 K dot ATM V2, right? And now I'm going to take that number and I'm going to divide it under there. And when I do, V2 equals 1.55 liters. So there you go. That's how we got it. All right? So a little bit of Gay-Lussac, a little bit of Avogadro, a little bit of combined gas formula. If there are any questions about this, we will definitely talk about them next time. And we'll see you later.